So for today's Meow seminar, we have the pleasure of listening to Bruno Cavalar, who will tell us about some of the very latest exciting news in circuit complexity about the monotone circuit complexity of matching. Please, Bruno, take it away.
Thank you. Yeah, so this is joint work with Mika, Artur, Anastasia, and Dmitry. So let's get started. Um, so computational complexity is like the other side of algorithms. You could say the algorithms and the study of algorithms is trying to harness the power of computation to do more things, and computational complexity tries to understand what are the limits of computation. Uh, The central question of the field is the P versus NP problem, which is about the inexistence of polynomial time algorithms for NP problems. And one way of approaching this problem is by means of Boolean circuits. Boolean circuit is a direct cyclic graph um, um, with some inputs, the source with some vertices, which are the source vertices, which are called inputs. They're labeled with literals. We have other vertices, which are labeled with logical operations or end, and we have one sink, which is the output gate. Okay, and it's known that it's enough to show lower bounds on the size of circuits, and size here means the number of gates that are necessary to compute a function in NP. Okay, um, but proving like lower bounds of the size of the type 10n is to an open problem. If any of this isn't clear, please interrupt me. Okay. Right, and monotone circuits are a variant of circuits which do not have negation gates. And you could be motivated to like look at this question of restricted circuit models just by this fact I just mentioned that, getting any progress has been so hard. So let's try to look at sub-problems that are easier. And a monotone circuit model is one of those models that have been successful proving lower bounds. And they are complete in the sense that every monotone function has a monotone circuit. And here, a monotone function is a function such that if you flip a bit from 0 to 1 and you accepted the input, it will continue to accept it. So think of it like computing, deciding if a graph has a click. If you add more edges, it will continue to have that click. Okay. Monotone computations, besides this interesting like lower bounds, has appeared in many areas of computational complexity. Earlier results in the 1990s have shown that monotone complexity is, in a sense, equivalent to the communication complexity of search problems. And also, if you show lower bounds on the monotone circuit complexity of certain functions, you also get lower bounds on the runtime of certain types of SAT solvers and certain types of optimization algorithms. These connections have been explored further in recent works, and this is a very, very nice survey about this. But in this talk, we'll be looking at particularly at the perfect matching function. So matching is just a collection of edges which are all disjoint. Um, and a perfect matching is a matching that covers all the vertices of the graph. And here we're particularly concerned only with bipartite graphs. Okay, so we want to decide if a complete bipartite graph, which received as an input, if it contains a perfect matching. Okay, so this is the matching function, and the way we are representing this as a Boolean function is we're receiving as input the entire adjacency matrix of the graph. So every bit is denoting whether a particular potential edge is appearing in the graph or not. And this match functions is known to be computed in like um, um, efficiently in parallel time. In particular, it's also computable in P. So it's a problem we know how to solve in practice. We have plenty of algorithms for this, even randomized algorithms that are even more efficient. But here's trying to understand what is the monotone complexity of matching. how much size do we require to compute the complexity to compute perfect matching. Just so like I mean I know some of you are very familiar with this, but maybe not all of you. So just to practice a little bit, it's easy to show an n factorial upper bound for computing matching. I mean, if you just wanted to compute to do the most trivial algorithm, what you would do is just try everything, try every potential perfect matching, try every permutation, and you can simply encode that as a monotone circuit. Okay, and it's going to be roughly the size n factorial because you do a big OR over all the potential perfect matchings, and then you check if all these edges of that perfect matching are present. Okay. Any questions about this? Good. And just some observation, can you prove that should 2 to the n using Hall's theorem? Okay, so what about lower bounds? So in 1985, Razborov
Is that
already showed.
Hall's theorem thing easy to see, by the way? Maybe it is.
Um, yes, I mean, you would try every. What the Hall's theorem is saying is that there's a perfect matching if and only if, like for every collection of vertices S, the neighbors of S is higher than the size of S. Right? So you can just go through all such sets, and there are 2 to the n of them, and then you can check if their neighborhood is larger than the size of the set itself. And you can do this kind of computation about size in monotone circuits.
Ah, okay. Yes, yes, yes. Thanks.
Good. Good. Thanks for the question. So as I was going to say, so Razborov showed in 1985, and this is Razborov in the 80s, he showed that you do require n to the log n size to compute matching. So there's already a gap, right? If monotone circuit, of general circuits, you can do this if polynomial size, but you require quasi-polynomial size to compute matching with monotone circuits. And the question that has haunted us since then is whether this is optimal. Um, It has been asked as a research problem by Yukna in his textbook. Um, More recently, Avi also in his textbook has mentioned it's an interesting fact that we don't know whether exponential monotone circuits are required to compute this problem. My co-author Mika has been promoting this problem for a long time. So this is him maybe 7 years ago in the right, and more recently Simon's talking, but including it as a holy trinity of problems he wasn't able to solve thus far. But here in the what we show is indeed matching does require exponential size to be computed. And there are some interesting consequences from this as well. I mean, this gives a simpler exponential gap between monotone and general circuits. So Tardas, already 98, proved that this gap between monotone and non-monotone circuits that's given by matching, which is quasi-polynomial by Razborov, can be shown to be exponential, but it requires function that is computed by semi-definite programming. But here we are able um, to apply our techniques, show our bound outs for a function which is in log space, which is even simpler than matching by reduction to connectivity. I may have time to talk more about this later on. Just because of those connections I mentioned before, this gives you new hard instances for types of SAT solvers, those that are resolution based, and new separations in the communication world of TF&P, because n to the log n, if you just take the logarithm, that's polylog, which is considered efficient for TF&P. So there's not only a quantitative meaning to this exponential bound, but even one could say a qualitative meaning. Okay, so why did it take so long? One potential explanation it could give is because right in the beginning, when all these lower bounds were shown for different kinds of monotone functions, and this method that Razborov created was developed by the community, people discovered this sort of symmetric approximation method. And as Yukina mentions here in the textbook, you don't need to read all of this, but just the part I here highlighted, this symmetric perspective captures every monotone function except perfect matching. So it seemed that perfect matching was this odd one out, which you could only show a lower bound for using Razborov's techniques and using a tailored method. Uh, I guess the first rays of light, I guess, but at least in retrospect, we can see uh, were shown by Rossmann in 2010 when he obtained new monotone circular bounds by introducing this thing called robust sunflowers, which we'll see in a minute. So you can think of this like a flower, which is like what he introduced and, um, and became very useful later on in combinatorics as well. And I went to visit Ben like 5 years ago, and together with Mirna, we showed improved monotone circular bounds. And this is like a photo of a whiteboard 5 or 6 years ago. And you can even see some flowers there. But it seemed that this wasn't obviously useful for several like properties that the perfect matching function had. But at least I, I could see that this if you took this approach of monotone circular bounds from robust sunflowers that Rosman developed, you could solve that little problem of Yukina of making sure that matching wasn't the odd one out. You could say that there's one approach to get all monotone circular bounds, and this is like very abstract. We could just get some abstract approximation method with abstracts sunflowers that could capture everything, including matching. But this didn't seem useful at all, just seemed like a, curiosity. And I thought you could just put that in this old book and forget about it. Um, but turns out this was almost enough. You just needed a new trick that was floating around, perhaps you could say, in several recent papers. And here, this wizard is holding the book, but she also has a new idea in her hand. And I hope to talk about both of them in the next few minutes. So let's revisit what is the approximation method and how it is an approach for this problem. Any questions so far? Good. So the approximation method works as follows. You're going to take a monotone circuit and you're going to approximate it by a DNF, which is the simplest kind of circuit you could imagine. So this DNF we just saw before when we construct this n factorial size monotone circuit for matching. And basically what it's doing is checking whether certain blocks of inputs are all ones. We're going to think about them a little bit more if this is not clear. But the method works by defining a set of instances, D0 and D1. You have to reject D0, accept D1. And because these DNFs are very simple, you can easily show that small monotone DNFs must make a lot of errors when computing on this set of inputs. But the crux of the approximation method is showing that with a small circuit, you can obtain a small monotone DNF, which has basically the same behavior on your test inputs. And because those small monotone DNFs make a lot of errors, then you also conclude that small circuits make a lot of errors. Okay? Okay. So just to understand what we're going to see and understand what monotone DNFs actually do when they are computing, let's just take a deeper look into this. So let's say you have a DNF. You have an OR of these terms TS, which are conjunctions of all the literals which are in the set S, okay? This term is accepting an input X if and only if X is coloring, you could say, all the entries of S with ones, okay? You could take also like a more of a hypergraph perspective, and you can think of X as a set, as a subset of the set of literals, and it's being accepted by the term S if S is contained in X. Okay. So from this hypergraph perspective, the DNF is accepting an input X if and only if this X, when viewed as a coloring of all the entries here, is coloring some hyperedge of the uh, hypergraph with all ones. Equivalently, it's rejecting an input X if X is independent in the hypergraph. Contains, this doesn't happen. Okay. So just an exercise, if your hypergraph contains the empty set, then you have the constant one function, right? Because this relation is always satisfied. Or in other words, you can always color with all ones because there's nothing to color. Okay? Right. So, but the question we want to understand is how we can approximate monotone circuits by DNFs. And the crucial step that we have to be concerned about is how we can take a large DNF and approximate it by a smaller one. Okay, so when you begin with this monotone circuit, let me just go back a bit. Here you already have a DNF by definition, right? You have an OR of two things. You also have a DNF. You have a which is small because there's only two things. You have AND, the same thing. But if you continue doing this over and over again, at some point you're gonna get a DNF which is very big, which is not small anymore. So how do you go back to being or restore the property of being a small DNF? So the question we have to ask is, when can a large DNF be approximated by a smaller one? And here we just choose, for intuition, concerned with the uniform distribution. Okay. Or equivalently, when can we find a smaller hypergraph such that the probability that a random coloring is coloring everything with ones or blacks, if you identify ones with blacks, and with roughly the same probability. Okay. Any questions about what we're trying to do? Okay. So suppose that just to begin with, you have a very large one uniform hypergraph. So your hyperedges are just a subset of the vertices. Which smaller hypergraph has a black hyperedge with roughly the same probability as the original hypergraph? I guess I'm offering participation. Maybe you can already see on the slide, right? I think it's hidden, but you can actually see. So I mean, it's also maybe it's also simple because when you have a large one uniform hypergraph, one vertex is colored black with very high probability, right? So you just the hypergraph, the empty with has an empty edge approximates it. We can think of equivalently in terms of DNF. We have just a norm of a lot of literals. Then this is almost always one over an uniform input, right? So you can just approximate it with the one, constant one function. Okay. Now we can ask the same question, just going beyond in the hierarchy of hypergraphs, and supposing we have a two uniform hypergraph, but again the edges are disjoint. Well, for the same reason, because they're all disjoint, one of them for sure is going to be colored all once. So you can just approximate it with the hypergraph that has the empty set. But now let's go to more interesting cases. Suppose we have a large star graph. Okay. Which smaller hypergraph has a black hyperedge with roughly the same probability? Yeah, so it's the hypergraph which has just these vertex as a singleton edge. Why is it? Well, because just as we had before, one of those vertices outside of the core of the star will, with very high probability, be colored 1, right? Because there are lots of them and they're disjoint. So everything you need to do to get a black hyperedge or all-ones hyperedge is to color V with 1. So it's sufficient with high probability to color V with 1. And at the same time, it is necessary because all of the edges contain these guys, so you need to color this with 1, right? So what I just said, uh, it is sufficient. So with high probability, there exists an edge which, if you remove the vertex V, it's going to be black. Okay? And it's also necessary because V is contained in all the edges. So you can just approximate this DNF, which is represented by this graph, which is just the OR of these ends here by just this literal. Okay, please interrupt me because I mean I'm hoping that this is helping to build intuition, and if this doesn't make sense, then nothing else will make sense.
I don't know. Is it like it was not clear to me how an empty graph can contain a black hyperedge, but maybe this is a more of a philosophical question. I mean, this
Yeah,
case is easier to see for me where I mean, I guess I should think of the central vertex as a very small sunflower, kind of,
yeah,
or the sorry, the core of a sunflower.
yeah. Um, So you're saying how a black? Oh yeah, I mean it's just by vacuity because if you have an edge which is empty, and your condition of satisfiability is that you have to color every vertex of that
In the
hyperledge with
edge,
once,
black.
and
Okay,
the
so
edge black.
vacuum, like, okay.
Yeah,
Okay, I see. Yes.
right. Yeah, and the other intuition I was trying to give is that you can think of this as having to satisfy this condition. The empty set is contained in your input. And that's always satisfied. Every input contains the empty set. Yeah. Does that make sense? Yeah.
Yes, I think so.
Okay, good. Good. Now we're going to generalize this. We're going to go to hypergraphs, and we're going to see what are actually robust sunflowers. Then robust sunflowers are just generalizing this um, to hypergraphs. So we have here S is a family of sets with at least 2 sets, and you're going to say that it's an absolute robust sunflower if exactly this condition here generalized holds. So if there exists a hyperedge such that it is black outside of the core with high probability, right? So in other words, you always need to color the core to get a black hyperedge. And if you color it with high probability, one of the hyperedges is colored black as well. Um, yeah, and it's necessary exactly because the core is the common intersection of all the elements. And this means that in terms of DNFs, we can just replace this DNF or of TS, or or of all these hyperedges by just the core term. And the approximation error is going to be at most epsilon. Great. Right, and there's robust flow lemma. So this is showing us how we can approximate some like DNFs which have this particular structure. They have this guy here and this core and all these hyperedges which are intersecting there. But you can also the robust flower lemmas allows us to do this for every um, hypergraph. So if your set if your family is large enough, then it contains a robust sunflower. This is what the robust sunflower lemma is saying. So what you can do is just you find this robust sunflower inside your family, and you replace it by the core, and thus you reduce the size, right? And now there's a technicality, but we were supposing that uh, it's important that the family has at least two guys. So yeah, you were gonna put this guy back, but then you're removing at least two. Okay.
So at this point, you're not elaborating on the difference between proper sunflowers and robust sunflowers. And they sort of also, if you looked at the properties you have, that as soon as you satisfy the core, you're likely to satisfy some petal. I guess that the way you to write that will be true for standard sunflowers also. But if you only need them robust, then you can expect them to get like more advantageous parameters.
Yes, that's precisely what happens. So here I have this bound, which is the tight bound for robust sunflowers. Uh, that was given by always Lovett Wenzang and Anna Perau. Um, no need to be too concerned with this number here, but this is like a bound for finding robust sunflowers in L uniform hypergraphs. And if you want to find something like this using just like traditional sunflowers, you're going to pay this factor, which is exponentially worse. So basically, there's going to be a 2 to the L inside this parenthesis here. And this harms a lot on the lower bound. I mean, this is what basically what makes Razborov's lower bound quasi-polynomial. Yeah, yeah. So
Okay, thanks.
yeah, so this is the core. This is just this is the approximation method from the perspective of robust sunflowers over the uniform distribution. Okay, uh, you have these DNFs. If your DNF is too big, find a robust sunflower. Replace all the terms of the robust sunflower by the core. Continue doing this until you get a small DNF. Because you can play with the parameter epsilon, you can make it like small. You're gonna make just epsilon error, which is basically epsilon is the lower bound you want to get at the end. And yeah, this is the approximation method. And this is showing then best as possible bounds on how big a family has to be to contain a sunflower structure like this is a combinatorial crux of these lower bounds. Show a lower bound here or show an upper bound, or depends how we phrase it, you get a lower bound for monotone circuits. Okay. Let's now switch gears to understand how this plays out in the setting of perfect matching. Um, so I was working on another problem, and I think some of you may remember I was very interested in this problem about AC0 and monotone circuits. Maybe I'll have time to talk about it at the end. And 2 years ago, I came to visit um, Lund and Copenhagen. And I was thinking about those ideas, and I was so excited because I thought I was going to show the this is very near. This is happening, and this is me in the Lund guest house, falling asleep with my notebooks. Uh, some of you may remember it was a very intense 2 weeks. But now, yeah. So now we're going to see what is it that uh, made me so excited. So our test inputs is the inputs where the monotone circuit must be correct when computing perfect matching. They're going to be considered first. D1, which is a uniformly chosen perfect matching. Okay, that's simple. And D0 is going to be as follows. We're going to sample a coloring of the vertices of the bipartite graph. Some are going to be here black, some are going to be white. And we are going to not only sample uniformly at random, but sample uniformly at random from the colorings that have an odd number of ones. And you're going to join vertices that have the same color. Okay. Now, why, so let's just, before I go, why is this a negative distribution? Why should this graph not have a perfect matching? Well, because these connected components have an odd number of vertices, so it cannot have a matching, a perfect match. Okay. Right. So how do DNFs behave on those graphs? Let's remember that in the context of perfect matching, every input is denoting whether an edge is appearing in the graph or not. So, okay, just remembering that C is the random coloring, X is the resulting graph. When you have when you say that the term TS accepts an input X of this form, you are actually saying that every edge of S is monochromatic under this coloring, because edges only appear on the when the two endpoints are colored with the same color. So the term TS is accepted if and only if every edge in it is monochromatic under the coloring. That's what's represented by this figure. You have here in red and bold the edges of S, and they're all monochromatic. All the endpoints have the same color. And here we have uh, um, the term TM rejecting X, precisely because there's an edge here which is not monochromatic. Is that clear? Yeah. So this DNF accepts X then, if and only if there exists a graph in this set of graphs here, which is, what is this? Which is monochromatic under the coloring. And here, I think I want to say that we are going to consider in only M, which is sets of matchings. So our DNFs, we only have terms that are matchings. I guess this is clear why we did for some of you, because I mean, we also we have to you know, be correct or accept, like our accepting inputs are perfect matchings. So if your term is not a matching, you can just remove it. You're going to make no mistakes here, because subgraphs are perfect matchings are all matchings. Okay. So okay, I just copied what I had before. So this DNF is accepting this D0 distribution if and only if there exists a monochromatic matching under the coloring C. So what would be a sunflower in this context? Well, we have these hyperedges, but now what they have are matchings inside them, right? And we want that um, there is a matching which is all of its whose edges are monochromatic outside of a core K, right? Because this is saying this core K of matching of edges in a matching, it's necessary to make them monochromatic for the whole matching to be monochromatic. And moreover, we would like to have the property that if this is monochromatic colored, then one of the matching is also monochromatic. And this means that we have low approximation error. And we can define the set of partial matchings to have precisely this property. Say the set of partial matchings and epsilon match in sunflower, if and only if there exists a match in the family, such that for every edge in the matching outside of the core, the edge is monochromatic, another coloring. Are we okay with this definition? I think this is this is the kind of key, almost, yeah, the key idea in a sense, or one of the two key ideas. They're stating that this definition, this matching sunflower definition, is what you need to approximate monotone circuits on the distributions I gave with DNFs. please feel free to interrupt, and I can go back the slides. We have more time later on, so you don't need to be afraid of making me go back. So okay, so just like before, I said robust sunflower bounds are what give you monotone circular bounds, and here matching sunflower bounds is what give you monotone circular bounds for perfect matching. So suppose then you have a set of matchings, all of which have L edges. The technical part, don't care too much about these numbers for now, is like a bound on how big a family must be to have an epsilon matching sunflower. And the only reason I'm showing you this is because you can rephrase Razborov's argument as showing that a family of this size contains an epsilon matching sunflower using the traditional standard sunflowers that Jakob was talking about and another trick, but you get this exponential blow up on the bound. So it's exactly this exponential improvement that we give, which allows us to obtain a better bound. And perhaps surprisingly, the proof goes by reduction to robust sunflower lemma. So let's see what would be a naive attempt to apply the robust sunflower lemma in this context. You could, well, what you want is that under a random coloring, the edges are monochromatic. So what you want is that everything here is colored either 1, 1, or 0, 0, 0, 0, or 1, 1, 1. Everything's colored monochromatically, right? You could just ignore the edges and find a robust sunflower in the vertex set of the matchings, and you're going to find some core K, right? What is the problem with this? Um, you know, let me just say before why this looks promising, because if you color everything with ones in the vertices with just finding a robust sunflower, everything's going to be color 1, right? Everything's going to be color 1, and that's even more than you want. You just wanted monochromatic, and now you're getting everything ones. That's even nicer. So you could think that you're done by just finding a robust sunflower, but you are not, because this core may not be matching. All you know is a set of vertices. For instance, it could be just 3 vertices, and then how can this be a matching? This cannot be a matching. But suppose it is 4 vertices or something, or you could massage into an even number of vertices. You don't know how to match those edges. So maybe in this red matching, you're getting these edges. But maybe in the green matching, you're getting these edges, right? Even though we have the same vertex set, you have different matchings. And it could be even worse than that. It could be like something like here this vertex is matched to this vertex in this matching, but in this other matching it's matched to this other vertex. So how do you transform this into a actual core? Okay, so yeah, so the problem is that K is not necessarily a matching, and we want to solve this problem. And here where we get this magic trick, and that's going to make everything work. So what I mean, it turns out that all it suffices for us is to consider only blocky families. So what are blocky families? Well, you have, remember that we are assuming that every matching has L edges, right? And what you're going to do is you're going to color it with, color the vertices of the bipartite graph with L colors, okay? And you say that a matching is consistent with a coloring like this if every edge of the matching its endpoints receive the same color. Okay, in other words, they're like in the same block. So we divided all the vertices into L blocks. So this is supposed to be representing L, like L blocks. Every edge, its vertices are on the same block, and moreover, every edge is in a distinct block. Right. So what is happening is that every block receives one edge and one edge only exactly from the matching. So this is what it means for a matching to be consistent with a block, with a coloring of the vertices. And by a simple average argument, we can show that there exists a coloring which is consistent with a very large fraction of the set of matchings. So we can just suppose that we are dealing with a blocky family anyway, and try to show that we can find an edge like an all ones, or rather a monochromatic matching outside of some core under this assumption. Okay. So we do like we did in the naive argument, and we begin with we take the set of vertices of the matchings, and what is interesting is that those vertices are in the set of vertices, the set of matchings, they are in one-to-one correspondence now, because as I said before, every edge is in precisely one block. So if you have this vertex and this vertex in your matching, then you necessarily need to have this edge, right? It never happens that you have, like, I don't know, this and this and this, for instance, in your matching. It's always two vertices from each block and those vertices connected, right? So just choosing two vertices corresponds to choosing this edge in your matching. Now we can find an epsilon robust sunflower in the set of vertices, as we wanted to do in the naive argument. So what is happening here? We have an epsilon robust sunflower on the vertices with a core. And just for simplicity, we have this core with these 6 vertices, A, B, C, D, E, F. So in the core, we have these 2 vertices, so this edge is necessarily present, and here the same thing. Here, this core has no vertices here, so every edge is possible. And here, the core has only one vertex on this part, so all of those edges are possible in the sunflower. So we take we take all the matchings that are associated with this sunflower, and what is interesting again is that there's no ambiguity on how to match the core vertices. At least because, like, what is going to be the core? We're going to take all the edges that appear in the core. So all the vertices that appear in twice, like rather every block that has 2 vertices, we take these 2 vertices and put them in the core of our sunflower, or intended matching sunflower. And the claim is just that these matchings which are associated with the vertex set given by robust sunflower is an epsilon matching sunflower with this core D. Right? So we're basically, as a bound on the matching sunflower, we're getting the robust sunflower bound plus what we paid for the averaging argument for the blocking, to get in the blocking.
Did we lose your slides, or was this only me?
Oh, did you?
I see the slides. Yeah, I see the slide.
think you're muted.
So yes, so let's see. So what do you do with the green and the orange? I mean,
Mhm.
the orange you're not doing anything with, but the green guy you can just
Yeah, so
ignore,
yeah, that's the thing.
and the gray guy also, I guess, yeah.
Yeah. Um, so maybe that's a bit of trying to going towards actually showing that the matching sunflower that this actually gives you a matching sunflower, and we can see more details in the next part. But what is going to happen is, okay, these edges are going to be in the core, and what the sunflower, robust sunflower guarantees for you is that um, um, there's going to be a set of vertices, like a set of vertices that coming from these matchings, which are going to be colored 1 here. They're going to be colored 1, 1 here, and they're going to be colored 1 here. Okay, so I mean, these guys we don't need to care because and they're going to be colored 1 outside of these vertices, right? So these guys we don't need to care. They're going to be in our core. These guys are already colored monochromatic because you have the 1, 1. But now here, what you have to do is you're going to have a 1 here, but you could possibly that this is colored 0, but this is not something that is in our core. And then you have to do some trick. Maybe you won't believe it very, very quickly, but uh, oh, I think I lost the number. Um, okay, a lot of clicks.
I thought we were doing matching.
Yeah. All right. So what's going to happen then, as I was saying, is that everything's going to be colored 1 here, 1, 1 so these edges are satisfied, and here I have 1. Here we don't need to care because they are in the core. So what was going to happen if these guys are colored 1, then we are happy, right? But it could be that this is colored 0 because um, how do you say, the robust flower property says nothing about the color of the core vertices, right? And these are core vertices. So it could be that you have a 0 here and you have also a 0 here. But what you can do now is uh, condition on every possible coloring that you can have on these vertices. And then if this coloring that you conditioned on gets a 0, you're just going to sample these colors flipped. And this is also uniformly random coloring with the colors flipped. And then what you get from the robust flower property is that when this is 0, this is also going to be 0. And then you have a monochromatic coloring. It's just this trick, and everything works. I don't expect this to be super clear to everyone at this stage, but we may have some more time. But I guess we get a overall picture of what's going on. You take this this set of matchings, you find a blocky subfamily, you find a robust sunflower on it, and then you're going to have some core vertices that are in this way. You take all of those that form doubles, put them in your uh, matching core, and when you have to satisfy these guys, you just do some trick of flipping the colors, and everything is going to work fine. At least this is the claim. This is how the strategy goes. Okay. Uh, any more questions about this?
Just to get some intuition, Bruno, what are the size of these blocks?
Well, there is no restriction on the size. I mean, I'm just for simplicity, everything is drawn the same size. But what we actually do is just sample this coloring, this mapping to blockings uniformly at random. So it can be anything, the size of the blocks, as long as it is consistent with all the matchings we get.
Okay, thanks.
I think you can then go to a conclusion and think about open problems. I think open problem in this direction is really just to kind of to get the best possible lower bound. We mentioned that you can get an upper bound using Hall's theorem of 2 to the n, and now maybe this is the best possible. Maybe if you avoid the blocky thing, we can go from what we did, which is 2 to the n over 3 to 2 square root of n, but I don't know if you can do that. If you avoid doing this thing on vertices, maybe you can do better and go to the omega of n. I don't know exactly how to should show this, but there are just some ideas. Yeah. Okay. Thank you.
Thank you so much, Bruno. So let's open up the floor for questions. So one question maybe while others are thinking. So is it clear? Can you say something about why going via vertices and this blocky setup, but why is it easier than going via edges?
Well,
A bit-
yeah, so it doesn't, so what precisely would you be asking? Would you be asking something like, yeah, we have a set of edges which are from the matchings, and then we try to find a robust sunflower on them.
I guess that's what I mean. You want to find
Mhm,
the sunflower on the edges ultimately, and for some reason
Yeah,
it
let me go back.
for some reason you want to. The way I understood it, rightly or wrongly, is you find kind of a sunflower on the vertices instead, and then you have some extra tricks to somehow be able to get vertices and a matching from this.
Yes,
And there
yeah,
has to be a reason why this all these extra hoops make your life easier.
yeah. So the reason is because we are only able to, at least I was only able to, and we were only able to show lower bound. You considering this distribution D0, and this distribution D0 is all about uh, the randomness is on the vertices. You're sampling a color for each vertex, and an edge is present if and only if the endpoints, the end vertices, are colored with the same color. So what you actually are working on is on finding a coloring which keeps your matching monochromatic. In my monochromatic, I mean the vertices of the matching are monochromatic. Um, so it seems the only
Basically saying the
natural, yeah.
probability space
Hmm.
is really, really reasoning about the individual vertices and how you deal with them,
Yeah.
and
Hmm.
that's somehow it's natural for you to
Yeah.
this is what you know and you have to build on this, basically.
Yeah, I mean yes, exactly. And you are coloring vertices, and the all that the edges are doing is saying what the coloring on the vertices must satisfy, and it's must satisfy that on these edges you must have the same color. But the whole thing that we're doing is coloring vertices. So there isn't a similar randomness. I mean, you could define a inherited randomness on the edges, but it gets very complicated. Because I mean, as you may, you in particular, Jakob, may remember that if you have like, okay, a particular edge is going to appear probability 1/2 because that's the probability that these two vertices are colored with the same color and the same for another edge. But once you have like 4 edges that form a cycle like this, then they have some dependencies, and like the edges are not independent anymore. Whereas if you just talk about vertices, everything is independent and behaves nicely.
Makes a lot of sense. More questions from the audience? So do you have any, if you would place a bet, is it 2 to the n? Is that the right bound?
I would place a modest bet, just because I don't know. Yeah, maybe a more a bolder bet, but I don't see how to do it with current techniques.
So maybe another question also before we take a break. So what if we continue with the for those who are thinking about tuning in after the break for the technical hardcore part of the talk, can you give any teaser like what could we get to
Yeah.
know?
I think we could try to show this matching sunflower lemma in a clean way, and I felt like some of you were lost a bit. Maybe, yeah, that's what I was planning for. To do this cleanly, matching, taking the robust sunflower and everything. But if there are any particular things about the proof that like that you are curious about, I can also talk about that. But otherwise, this is the plan.
Sounds good. So we are about to take a break, the final chance to ask Bruno a question before we take a break. Going once, going twice. And I guess so. Thanks again, Bruno,
Thank you.
for the talk so far. Thank you. So we are back after the break, and it's over to Bruno again.
Thank you. So, what we would like to do now, you may have other questions, but we could just look at the proof of the match in sunflower with more care. So, let's just recall the definition, and then perhaps even if the definition itself is not super clear, we can yeah, talk about it. So we have this set. I'm just going to write F.
And just as a naive question while you're writing, I mean, any sunflower will be a robust sunflower simply because of all the petals are independent. It's like
Yeah.
highly unlikely that all of them turn out the wrong way.
Yeah, that might be nice to see. So if you have like a S is sunflower with R petals. So here I'm talking about S being, and here the sets are truly disjoint. Okay,
Mm-hmm.
you have this set K. So what you want is to understand like what is the probability when you take this random X that for all S in the family, you get that this is not in X. Okay. This is what you want to at the end to get this utmost epsilon, right? Or in other words, like
Yeah, so this is when you pick up an approximation error because none
yeah,
of the original terms fired, but when you pick the core only, then you got a false positive now.
yeah. Right. So how do you calculate this? This is so because all these s minus k, they are disjoint. This is the same as, and like x is uniform. This is all these events are independent. So this is like and that's you know, something like you know, sunflowers are petals and they all have length L. To the minus L, the probability of no, this is actually this is 1 minus to the minus L, right? Because to the minus L's probability is contained in X, so this is the inverse. Okay, so like the probability that, I don't know if this is clear, but this is really, well, this is to the minus S minus K, right? Which is at least to the minus L, because they all have length L. Okay, so I'm just bounding this here, and this is minus R because there are guys in the product. And this is utmost epsilon if R is like 2 to the L log 1 over epsilon. The sunflower is like, for you to get this much, to get this many petals, you need R. Like even if you even have the sunflower conjecture true, you would need this to be R to the L, which is right. So you get a you get a epsilon robust sunflower from a sunflower with this many petals. Sure. Okay. Right. So we can go to, I mean, we kind of reviewed it now, but the epsilon robust sunflower, is this set S such that probability that exists some guy there, which you color 1 or once is at least 1 minus epsilon, where the core is just the common intersection. And you can define the epsilon matching, where now you have this coloring, and here we have over the vertices, there are 2 vertices on each side of the bipartite graph. And there exists, so family F, so there exists a matching such that every edge in the family, in the matching, is monochromatic. Okay. So how do we show a bound here? So the lemma for the robust sunflower is you need size some constant, this much to find epsilon robust sunflower in L uniform hypergraphs. Okay. So for the matching sunflower lemma.
Excuse me, can you
Yeah.
read the bound in words? Because I can't read it very well.
Sorry. Yeah. So I can try to write it again. So this is log L over epsilon to the L. Okay.
And the thing in front, is it a constant or what is this?
B is a constant. Yeah.
Okay, thank you.
B is universal constant. Okay, so how is the bound shown of the matching sunflower bound? So just right here, what we're going to get, we're going to get this. So let me actually just use here, denote this whole formula of the robust sunflower by like R L epsilon. Maybe this is not a good color, but this is R L epsilon. Okay. So we begin with this thing that I mentioned in the beginning. We sample B which is a partition of the vertices into L blocks, okay? Uniformly at random, okay? So what is the probability that an edge is colored with the same color? This is like, so just probability over B in V fixed. This is just 1 over L, right? Okay. You're choosing for each vertex a color 1 from 1 up to L. The probability that you have two guys are colored with the same color is 1 over L. Two fixed guys. So the probability that matching M, so this is just this whole thing here means consistent with B, that a whole matching M is consistent is 1 over L to L, right? Because I have L edges in the matching.
Do you not also need some constraint saying that different edges correspond to different colors?
Yeah, yes, that's true. So maybe I wasn't here so careful. So let's remember what he's saying, that we want these buckets, we want all the matchings to receive the edges receive the same color, but it also want them to be bucketed into different buckets or put into different blocks. Yeah, so because a different way of doing this calculation is just that there are like L over 2L blocks, L over 2L possible choices for B. And L of factorial of them are good, right? Because what you're doing is um, um, you're taking these edges and you're going to like permute them and decide which blocks they are going to go to, right? And this is L factorial choices, so you get this much. Right. And this is going to be basically like some constant. Okay. So this is just the average argument that I was mentioning. Like probability that random matching is consistent with the random coloring is big enough. So in particular, M, like our set of matchings, is consistent. Or rather, like some partition B is consistent with M, like this constant there. Matchings of M. Okay. Now, if you assume that M is like just the robust sunflower bound, and you add this constant and you add this L to the L factorial thing, then like this M star, like which you could say is like those that are consistent with this. Say that's M star. M star is at least the robust sunflower bound, and therefore contains an epsilon robust sunflower. Are we good so far? Good. So we are going to just concern ourselves with this M star family, and we are just going to, like, for simplicity, say that M star is just M, because we're never going to talk about M anymore. And just so you may remember then also, just in terms of like the actual value that you get in these things, this was this log L over epsilon. Basically there's a constant, but we're not concerned about this, L. And now I'm just going to say that we should have used 2L here. And can you say why? Just to test if you're following. Well, we need 2L because there are 2L vertices in a matching of L edges, right? And we're going to apply the robust flow lemma on the vertices, so we should actually have used there some 2L, but this is inconsequential. I'm just saying that every argument is going to add is just an L here to this L to the L to something that already had an L exponent, and this is not going to be hurtful. Okay. So now we are happy that we find this family that contains robust sunflower, and it's blocky, moreover. So do we remember the great properties that blocky families have? Because every matching has one edge exactly at each block. You know that if a matching has this vertex and this vertex, then it must have this edge, right? And moreover, it never happens that the matching is like this. This is not allowed. It doesn't happen that you have something like this as well. Okay. So so this M family contains an epsilon robust sunflower. Let's find this robust sunflower. What's going to happen? Well, you're going to find, okay, this has an epsilon robust sunflower. And let's draw the core vertices. So maybe you have 2 core vertices, and you have here 1 core vertex in this other block. So what happens is that every matching in the family, because every matching contains these 2 vertices, every matching in the sunflower contains these 2 vertices, it also contains this edge, right? Right, so just say that this A, B, and C, and the core is A, B, C. Okay. And all the other matchings, other edges in the matching, they can be like this, or they can be like this. But here, where you have the C, they have to be like this, right? Okay. So what does the robust sunflower property guarantee to you? Well, it guarantees, just going back here, that you're going to have everything colored 1 outside of the core vertices. Okay. So when you, what is the matching sunflower is going to give you? It's going to give you that with high probability there exists some matching. Let's draw this matching. This matching contains this edge here, contains some whatever edge in this block, contains some edge like this, matched to this vertex, and some edge here. What are going to be the colors of the vertices over this uniformly random coloring? Here you're going to get whatever, we don't know the colors on the block, on the core of the sunflower, but we know that here we're going to have 1s and 1s. That's what the robust sunflower property guarantees to us. We don't know what we get in the core, but we know what we get here. We get a 1. We also get a 1 and a 1. Right? What property we wanted to satisfy with the matching sunflower? We wanted that the matching had all the edges colored monochromatically. This is satisfied here. Everything is colored 1. This is maybe not satisfied here, but it doesn't matter because this is going to be a core edge. Remember that every vertex there are doubles. Whenever we have two vertices in the same block, we take the edge that matches them and put them in the core. So we don't care about satisfying these edges. Here, the same thing. The only problem is here. You have an edge, you have a 1 here, but you don't know the color of this vertex. Okay? Do we see this is the problem that we need to handle? Yeah. Good. What about you, Jakob? You were saying about this that you wasn't super clear, so wanted to ask you as well about this.
Yeah, so I would benefit from getting this explained again, yes. So
So from like this part, or from like the
so
monotone block?
so where are we now? We have
Mhm.
I mean, at the end of the day, we want to argue about edges, but you said everything is in terms of vertices.
Mhm.
So this blocky thing is to somehow say basically that if I can get a much larger robust sunflower in terms of vertices,
Mhm.
then my edges are also going to be okay
Yeah.
in the end. Is
Yeah.
that?
Yeah. This is the crucial kind of uh, the difficult part, I guess, because I have to switch from vertices to edges. So like an absolute robust sunflower is just saying it doesn't matter exactly where the randomness is, but uh, if you have um, uh, this random coloring of endpoints, then one of them is all ones outside some core, right? And now we're applying the robust sunflower on the set of vertices. And this means that we are getting uh, all ones on the blocks where there is no core vertex, and therefore the edges are monochromatic. By the edges being monochromatic, I mean that the two endpoints of the edge are colored the same color, right? Because
Mhm.
both color 1, then both the endpoints are colored the same color. And that's what we want. So in the blocks where there is no core vertex, everything's color 1, so it's monochromatic. In the blocks where you have two chord vertices, what you're going to do, because you know that this edge is necessarily there in your sunflower because of the blocky restriction, then
I
we're
mean,
just going to,
otherwise you wouldn't be consistent with the blocks, so
yes,
you would have filtered it away.
yes, exactly. Because of this, because you wouldn't be consistent, you can just put this edge in the core of your matching sunflower. So we don't need to satisfy the edges where both the endpoints are in the vertex sunflower core. So we don't need to satisfy these, and we don't need to satisfy these. The only thing we need to satisfy is this, is when you have a core vertex, which is its only vertex in the block.
Mhm.
And yeah, what's happening there is because we know by the robust sunflower property that an edge, sorry, that the vertices you're going to get here from the vertex sunflower, this guy is going to be colored 1, which is not the core, but the core we don't know the color.
Okay. So, um, so what do we do now? So,
Yeah, so we don't know the color of these guys. But what we do is we just partition over every coloring of the. So I'm just going to highlight this with some color. So this is single, right? Every coloring of the single vertices. Single core vertices, which are just like that one, like the highlighted yellow. Like they are the only core vertex in the block. So the random coloring is going to assign colors to these vertices as well. But the the catch is that, like, when you have something like this, okay, just like before, and let's say this is colored, well, if this is color 1, do we agree if you're happy? Because we know that this is going to be colored 1 as well, outside of the core, so we are happy. What we have to do is work with the case when this is 0. But what we're going to do is we're going to when we condition on this color being 0, we're going to sample every color in the block with its color flipped. So basically what you're doing is here, instead of just sampling some xi, you're going to sample one yi and XOR 1. And these for all the vertices in the block where the single core vertex is colored 0. Now, this is also uniform. Like if you sample colors and inside a certain block, you just flip the colors, it's fine, it's still uniform. But the robust sunflower property is going to tell us that xi is 1, which is like the same thing as yi is 0. So you are getting, so the y's are the coloring you want. Shall say actually. Yeah. Yeah, and surprisingly, this is yeah, this is everything you would need to complete the proof. I'm happy to explain again if some step is not very clear.
the one thing that which is a very basic question, but that we didn't talk about. Okay, so once you have the sunflower lemma,
Mm-hmm.
you will then run basically a standard approximation proof. Just go over the gates one by one and pick up the errors and carefully calculate how many errors you have
Yes.
and
Yeah, you're going to approximate with DNF, monotone DNF, as we discussed. And the DNF is going to have some width, which is like, I don't know, into the 1/3, more or less, which is coming from the limitations of the sunflower bound. And the number of terms is something like, yeah, some constant, yeah, entity epsilon L. Number of terms of with L. And there's another technical part that I didn't mention, which is kind of simple. So, I mean, when you do an OR, you have two DNFs. What you're going to get is a DNF of double size. Well, then what you just do is what we just discussed. You pluck matching sunflowers until small again. But it can happen that you also have an AND, and then if you have like this, DNF, which is an OR of AND, etc., you're going to get at the end big DNF with terms of doubled width. So the width increases as well. So what do? You just remove. I guess this is also like in many applications of approximation method, you do the same thing. You just remove terms of width, larger width. Like if some term crosses the width threshold that you set, which is here is going to be something like n to the 1/3, then just remove that term. And the reason you don't make a lot of mistakes is because the set of matchings are very spread. So basically, if you have a fixed like matching here of L edges, it's a matching M. So what is the mistake that you make when you remove this matching? This is the number of perfect matchings that contained this matching, right? So you just count number of perfect matchings P such that M contains P over the number of total perfect matchings total. This is going to be not a lot. This is going to decrease exponentially with L. So if your terms are too big, like there are too many edges, this is exponentially small, very, very small, so you don't make a lot of mistakes when removing those large width terms. So yeah, these are really the only two approximation steps: removing terms of large width and plucking matching sunflowers. Yeah. Happy to provide more clarifications.
I mean, I would need to think a bit more about how to go back and forth between vertices and edges, but this might be something that I need to do offline. I don't know if this question makes sense, but if you try to zoom out a bit and say, like, what is this? I mean, do you think what you did here, could it be useful for, like, is this a new technical tool? Can we use it for other things that also
Yeah,
are
that's a
not
nice
known?
question.
And also, you mentioned something about wait, what was this? Like a simpler separating example for, what
Yeah.
was this? L
Yeah,
versus something?
I can talk about this. So, regarding this question, I don't know. The only thing I could potentially think of, but I haven't thought very deeply, is whether this can also be applied for like purely combinatorial things. So you know these sunflower bounds, they are sorts of anti-concentration inequalities. And if you just think of, as you were asking about the edges, the probability that a certain edge appears in that graph where the you sample colors of the vertices, there are dependencies between these edges, but they, like whenever you have a forest, you have independence. So I just wonder whether if you want to study anti-concentration inequality for distributions, where the like the random variables have this sort of independence between them, using some of those ideas. But the thing I was going to possibly talk about is you know, like it's already known that we cannot simply or naively convert a monotone circular bound into a non-monotone circular bound because of Tardas and all those other separations. But you could ask whether you could still obtain non-monotone circular bounds from monotone circular bounds, particularly if you could like you can simulate P in monotone P, but maybe you can simulate smaller classes, and like more concretely, the smallest class you could try to simulate with P would be AC0. And AC0 here is a constant depth circuits, and which are a very simple model that cannot even compute parity. And this is a question of Grignon Sipser in 1990. And the problem, I mean, you could think that this is like not very helpful because we already have AC0 lower bounds, but a nice observation is just that if this is true, then NC2 is not equal to NC1. And so this becomes an interesting question on itself, like trying to understand if this simulation is possible. And what this work on matching shows is this actually is not possible. So there exists a monotone function in AC0 which cannot be computed by monotone circuits of polynomial size. And that's because our lower bound not only works for matching, but also for this odd factor function, which accepts if the graph, like every connected component, has an even number of vertices. This is monotone, right? Because if every connected component has an even number of vertices, you can add edges, you're going to join connected components, and you're going to continue having an even number of vertices. And this is also a problem in log space because you can just do like various invoke connectivity algorithm of Rango in log space many times and solve this problem. But what is interesting is that it accepts perfect matchings because perfect matchings, all connected components have an even number of vertices, but also it rejects the odd colorings we have been speaking about because the connected components have an odd number of vertices. So the lower bound also holds. But it is also true that if you have function in log space, then it can simulate it in AC0 if sub-exponential size. So basically you can do a padding trick. You have a fixed to the n to the 1/3 lower bound here. And here you can get a lower bound as small as upper bound as small as this much in AC0. So if you pad things and pad things properly, this becomes function AC0. And the lower bound is, it's quasi-poly monotone. So in particular, this rules out something that I never really believed much could be true, but I don't know. We had to rule out whether it was possible that you could simulate AC0 with polynomized monotone circuits. And this rules out this approach to break through circular bounds. So I guess you can sleep well at night knowing that there isn't a simple way to obtain those lower bounds.
Isn't that going to make us sleep worse at night?
Well, there's more work to do.
Thanks a lot, Bruno.
Thank you.
Do we have questions from other members of the audience? Before we call it a day. So maybe we already asked enough questions. I don't know, but I think seems like this might be a good place to say thank you again, Bruno, so much for
Thank
this
you.
presentation. Thanks a lot.
Thank you.